Welcome to the presentation of our paper, How Shift Equivariance Impacts Metric Learning for Instance Segmentation. Our work clarifies if the segmentation of identical objects with a metric learning model is feasible. In the literature, we found that it's infeasible due to the shift equivariance property of the employed CNNs. The problem is that shift equivariance results in CNNs always assigning the same embedding for identical objects. We investigated this and found that most often this doesn't hold, and units, for example, can learn to distinguish identical objects quite well. Our second contribution is that we show how stitching inconsistencies appear when doing Talent stitch inference with a unit on large images, and how to generally avoid them by cropping the output prior to stitching. We looked into the building blocks of the unit in order to clarify if it can distinguish identical objects. It consists of an encoder and a decoder path. In the encoder, the levels of the unit each consists of two convolutions followed by the activation function and a max pooling operation with window size 2 by 2. Here we have a small example image with 3 identical objects, and we just apply the pooling operations from the unit on it to show its effect. On the example image, we also show the grid lines of the downsampling grid. The windows resulting from the grid lines each end up as a single pixel in the respective level of the unit. As you might have already guessed, the upper two instances could easily be distinguished from the lower one after 1 or 2 pooling operations due to their distinct artifact patterns, but the upper two objects cannot be distinguished. Different artifact patterns occur for different positions relative to the downsampling grid, which is given for top versus bottom objects. In contrast, both objects at the top are at the identical relative position towards the grid, yielding identical artifact pattern and therefore cannot be distinguished. We then tested this with a toy data set consisting of identical disks that are regularly spaced. The unit that we used for this experiment had 3 levels. We proved that this network is only equivariant to pixel shifts that are multiples of f to the power of L, with f being the pooling window size and L being the number of pooling layers. For this particular unit, f to the power of L equals to 8 pixels, and this means that the network cannot distinguish object copies whose centers are multiples of 8 pixels apart from each other. We also proved that the network is non-equivariant to shifts that are not multiples of f to the power of L, and therefore it can distinguish identical objects when the object spacing is unequal f to the power of L. It's again because of the different artifact pattern that occur for most object spacings. In the video, you can see embeddings and predicted instances for various object spacings. As you see, most often the network predicts embeddings that easily distinguish the instances. This is less irrelevant in practice. We showed that adding small amounts of noise or elastic deformations is sufficient for the network to even distinguish identical objects spaced f to the power of L pixels apart from each other. Of high practical relevance is instead that inconsistencies at the tile boundaries occur when doing Talent stitch on large images. The grid shows a filter map in the bottleneck of the unit. The decoder path consists of 3 levels, each consisting of a transposed convolution upsampling operation with filter size 2 by 2 and 2 valid convolutions with filter size 3 by 3. Here again, we sketch an upsampling grid, where the pixels in the different levels of the upsampling hierarchy that influence the outputs are visible. Let's highlight the grid lines coming from the bottleneck and stitch the outputs. Naive tile and stitch inference leads to relative positions ending up next to each other at the stitching boundaries that won't up next to each other when passing in the whole image at once. It's there where the inconsistencies arise. When cropping the output before stitching to some multiple of f to the power of L, the stitched output is equivalent to output predicted when passing in the whole image at once. In the paper, we also proved this equivalence. We also tested our findings on real data. The video below shows the effect of different inference crop sizes on the number of false splits depicted in blue and the AP50 scores shown in red. The best performance is obtained for inference tile sizes that are multiples of f to the power of L, which is highlighted in gray. As we prove general properties of the unit, these findings also apply to a wide variety of other dense prediction tasks. Last but not least, we validated our findings on 2 other benchmark datasets. In the middle, you see the benchmark metrics for the Kaggle Data Science Bowl 2018 dataset, and on the bottom, you see them for the Nuclei 3D dataset. Metrics are calculated for the whole test sets, and the effect of correct tile and stitch on the number of fault splits and the AP50 scores is clearly visible in the plots. With this, we'd like to conclude and thank you for your attention.